A slow, cinematic opening describing the deep infrared darkness where light from the first stars sleeps beneath 13.5 billion years of silence. Narration drifts across the cosmic dawn, lingering on light so faint it has almost forgotten it was born. Then, the fracture. JWST detects something impossible in the earliest era of the universe. Galaxies too massive, too bright, too mature, appearing only 200 to 300 million years after the Big Bang. Light shaped not by youth but by ancientness, as if the universe had aged too quickly. A discovery that bends the arc of cosmology, whispering that the early universe was not what humanity believed. The tone shifts from awe to unease. If these galaxies are real, then something beyond current physics has been hiding in the dark. Maybe dark matter was different then. Maybe cosmic inflation did not unfold the way the textbooks say. Maybe the universe began with more structure than randomness. Maybe gravity behaved differently. Or perhaps the Big Bang itself was not a beginning, but the residue of something older. A mystery vast enough to undermine the foundations of cosmology. The hook ends with a philosophical tension. If the universe matured too fast, then the rules written into space-time are not the rules scientists have known. And JWST has become the first witness to this cosmic betrayal. In the cold architecture of the James Webb Space Telescope, every component carries the memory of a question humanity had not yet dared to answer. Its mirrors, gold-coated and hexagonal, were shaped not merely to gather light, but to bend time itself, pulling ancient photons out of the darkness where the first stars once flickered. Each segment was polished to atomic precision, a labyrinth of intention designed to see what had remained invisible since the birth of the cosmos. And at the heart of this vessel, buried within layers of shielding colder than the shadows of interstellar space, rested its purpose: infrared vision capable of reaching cosmic dawn. Infrared light, stretched beyond redness by the expansion of the universe, carries the oldest stories. It passes through cosmic dust, slips through the veils of collapsing stars, and escapes the gravitational pull of galaxies that formed before Earth existed. To see the first moments after the Big Bang, a telescope must do more than look. It must wait for light that has spent the age of everything traveling toward it. JWST was designed for that patience. Its sunshield, a 5-layered bloom of silver membranes, unfolded like a fragile metallic flower. Each sheet thinner than a strand of human hair, yet together able to cool the telescope to a temperature where heat itself becomes a kind of noise. Only then could the observatory open its silent eyes. Only then could it begin the work of witnessing the unseeable. On December 25, 2021, the telescope left Earth in a quiet ascent. The launch was without spectacle, no roaring crowds, no chaotic broadcast energy, only the steady rise of a machine whose destination lay a million miles away. As the rocket faded, the observatory entered a trajectory toward the L2 Lagrange point, a gravitational harbor where the Sun, Earth, and Moon hang in a delicate alignment. For 30 days, it drifted, adjusting its path with soft bursts of gas, almost a breathing motion, until it reached the stillness where it would remain for decades. There, in the deep exhale of the solar system, the unfolding began. Mirrors opened, joints rotated, the sunshield unfurled. It was a choreography of mechanisms rehearsed for nearly 2 decades, all for the moment when the telescope would finally face the past. When its instruments cooled and its sensors were calibrated, the first deep images were captured. They were not expected to change the world. They were meant to be test fields, routine observations, a cosmic calibration. But as the first pictures appeared on screens at the Space Telescope Science Institute, something unusual shimmered in the data. Galaxies, tiny and reddish, sprinkled across the image like embers scattered through night. They were fainter than whispering echoes, yet unmistakably bright compared to their distance. Their shapes were surprisingly compact, their light curiously mature. Scientists leaned closer. The room quieted, and for a moment, disbelief held the air perfectly still. The CRS collaboration, the Cosmic Evolution Early Release Science Survey, was among the first to examine these deep field structures. They ran initial photometric estimates, calculating redshifts based on color and brightness. Numbers appeared on screens: 10.2, 11.4. 12.3. Galaxies that formed just 300 million years after the Big Bang. Then even higher, candidates pushing redshifts beyond 13, where the universe was not yet a full 2% of its current age. At first, the reaction was simple confusion. These observations were deeper than any before, yet they were not expected to break the boundaries of theories so quickly. Surely something was off. An error in calibration, a photometric misinterpretation, a cosmic mirage. But then Cosmos Webb, another large survey, began detecting similar objects. Distant galaxies with startling luminosity and unexpected mass. JADES, the JWST Advanced Deep Extragalactic Survey, added more candidates, each confirming patterns the earlier instruments had glimpsed only faintly. And across these independent datasets, a truth began whispering through the silence. The early universe appeared to be far more crowded, far more structured than models predicted. The scientists who encountered these signatures were not fringe theorists or excitable optimists. They were some of the most respected names in early universe cosmology. Brant Robertson, whose work helped define the limits of star formation in young galaxies, was among the first to publish analyses suggesting these objects were simply too massive too soon. Emma Curtis-Lake, analyzing NIR-SPEC spectra, began identifying elements and ionization patterns inconsistent with naive expectations of primordial youth. Stephen Finkelstein and Rebecca Larson, both leading figures in deep-field astrophysics, traced these galaxies across multiple wavelengths, confirming that what JWST saw was real. Their papers surfaced on AR-14 like stones breaking through the calm surface of cosmology. Each one contained phrases that had rarely appeared in serious astronomical literature before. Overly massive, overly compact, surprisingly evolved, unexpected brightness, premature galactic maturity. These were not poetic exaggerations. These were expressions of scientific unease, written into technical analysis. At the center of this puzzle lay the galaxies themselves. Some appeared to contain as much mass as the Milky Way, yet had formed in only a few 100 million years. Others displayed stellar populations that suggested multiple generations of stars had already lived and died. There were even candidates with intense ultraviolet radiation, hinting at black holes growing at ferocious rates. These signatures contradicted nearly every simulation of galaxy formation. In the Lambda CDM model, the current standard of cosmology, structure formation takes time. Gravity must gather diffuse matter into halos, gas must collapse into stars, supernovae must enrich the environment, and black holes must slowly accumulate mass. Yet, JWST was showing galaxies that had apparently completed these steps before the universe was ready for them. The initial response was cautious skepticism. Large astrophysical surveys often produce false positives, and photometric redshifts can be misleading when galaxies are dusty or unusually bright. Many suspected these objects were simply closer than they appeared, or gravitationally lensed by unseen neighbors. But spectroscopy changed everything. When NR-SPEC captured detailed spectra, the redshifts held firm. Emission lines confirmed their distances, their ages, their impossible maturity. Repeated confirmations across JWST, JADES, and Cosmos Webb sharpened the picture. The early universe was not an empty sea slowly filling with islands of matter. It was instead a storm of rapid assembly, a cosmic landscape far more aggressive and efficient than theory allowed. In meeting rooms across institutions, from the University of Texas to Cambridge to the European Southern Observatory, scientists discussed these findings with a mixture of excitement and discomfort. What began as curiosity grew into a widening unease. If these galaxies were truly this ancient and massive, then something was wrong with the foundations of cosmology. Perhaps dark matter behaved differently in early epochs. Perhaps inflation left behind pockets of overdense regions that grew rapidly. Perhaps black holes formed not slowly but explosively through primordial mechanisms no telescope had ever witnessed. Or perhaps, as some dared to whisper, the universe carried hidden structure, an imprint from before the Big Bang. But those were questions for later. For now, the discovery phase had delivered its truth. JWST had seen galaxies that should not exist. Galaxies that defied timelines. Galaxies that forced cosmologists to re-examine their most trusted models. The early universe, once imagined as a gentle dawn, was revealing itself as something more dramatic and unfamiliar. A place where light rose faster, structure grew sooner, and the cosmos was far less patient than anyone expected. And somewhere beyond those ancient red horizons, the real mystery waited. In the weeks following JWST's earliest deep-field releases, a quiet disturbance began to ripple through the scientific world. It did not emerge with the force of loud public announcements or sweeping headlines. Instead, it unfolded like a subtle shiver running beneath the surface of cosmology itself, an unease that started in private conversations, in draft manuscripts, in late-night teleconferences where researchers spoke more slowly than usual, choosing their words with care. Something in the data was refusing to align with the comforting shape of the known universe. The contradiction had been whispered since the first high redshift candidates appeared, but now it became undeniable. The Lambda CDM model, the reigning framework of modern cosmology, offered a timeline shaped by cold dark matter, by gradual gravitational assembly, by star formation that trickled into existence like dew settling on ancient stone. According to this model, the early universe should have been a quiet, nearly featureless expanse. Gas should have been sparse, stars should have been primitive, and galaxies, if present at all, should have been fragile structures still learning how to shine. Yet JWST was showing something else. Some galaxies appeared to possess masses rivaling the modern Milky Way, even though they existed when the universe was less than 400 million years old. Their light was startlingly intense, filled with ultraviolet signatures that implied dense clusters of young stars. Others carried hints of mature chemical enrichment, elements heavier than helium, despite the fact that such elements should require multiple generations of stellar birth and death to accumulate. Their profiles suggested symmetry, rotation, even bulges and disks more akin to galaxies that had evolved for billions of years. These were not the faint, trembling sparks cosmology expected. They were luminous, compact furnaces of matter burning far too brightly for their place in time. As evidence mounted, the shockwave began its journey through institutions worldwide. At universities, researchers printed JWST spectra and pinned them to white boards. They circled peaks and dips in the data, comparing them to simulations from Illustris G, Eagle, and Renaissance, massive computational efforts designed to reproduce cosmic evolution from the Big Bang to the present. But the simulations, despite their sophistication, had never produced galaxies like these at such early epochs. Not even in their most extreme runs. The standard model of cosmology seemed to be faltering under the weight of what JWST was revealing. In the Lambda CDM framework, dark matter forms the invisible scaffolding of the universe. Its clumps, called halos, emerge as small seeds soon after the Big Bang. Gas falls into these halos slowly, cooling gradually, condensing gradually, forming the first stars gradually. Everything in the model moves with caution, as if the cosmos itself respects some universal rhythm that prevents haste. But JWST's galaxies did not respect that rhythm. They seemed to have formed before the universe had time to obey its own rules. For many cosmologists, this was the most troubling element. The discrepancy was not minor or cosmetic. It struck at the heart of the timeline that underpinned the Big Bang model. If galaxies this massive existed so early, then dark matter halos must have grown faster than predicted. Or gravity must have acted more efficiently, compressing matter with a force not accounted for in current equations. Or the cooling processes that govern the birth of stars must have occurred with a speed unknown to physics. And if none of those explanations were sufficient, then something even more dramatic might be at stake. The timeline of the early universe itself could be wrong. Some researchers proposed that cosmic expansion may have behaved differently in the first few 100 million years, shortening or altering the visible age of the cosmos at high redshifts. Others suggested that the primordial density fluctuations might have been far more extreme than inflationary models allowed, creating pockets of the universe where structure formed with unnatural haste. Then came the more speculative hypotheses, ideas that blurred the line between established physics and the frontier of the unknown. One possibility involved dark stars, hypothetical objects powered not by nuclear fusion but by the annihilation of dark matter particles. Such stars, if they existed, could grow to enormous sizes in the early universe and shine with unearthly brightness. JWST, with its infrared sensitivity, might be detecting these exotic beacons masquerading as ordinary galaxies. Another idea resurrected old discussions about primordial black holes, objects formed not from dying stars but from density spikes in the first seconds after the Big Bang. These black holes could act as gravitational seeds, pulling in matter with extreme efficiency and building galaxies far more quickly than standard models predicted. In this scenario, early supermassive black holes might not be cosmic anomalies, they might be the architects of the first galaxies. A third thread of speculation suggested that the earliest epochs might have experienced a phenomenon known as black hole-assisted structure formation, in which ultramassive seeds created violent local gravitational wells, condensing gas into stars at terrifying speed. Each theory felt bold, even unsettling, and yet each was crafted with a delicate scientific restraint. No one was rewriting the laws of physics, not yet, but many were running their fingers along the edges of those laws, searching for fractures. The tension deepened when researchers compared JWST's findings to predictions from Big Bang nucleosynthesis. According to this well-tested theory, the early universe produced primarily hydrogen and helium with only trace amounts of lithium. Heavier elements, carbon, oxygen, iron, must arise from stellar furnaces over long periods. But some of JWST's galaxies emitted signatures that hinted at unexpected enrichment, not fully mature, but far ahead of the expected schedule. If these were true detections, then entire generations of stars must have lived, burned, and died in cosmic intervals far shorter than theory allowed. This violated another boundary, general relativity's structure formation limits. Einstein's equations, when combined with the cosmological constant, place constraints on how quickly matter can clump together. But JWST's observations seem to push against, or perhaps even beyond, those constraints. The shock to the scientific community was not theatrical. It was quiet, contemplative, almost reverent. Cosmology is a discipline accustomed to mystery, but not to contradiction. And yet here was contradiction presented through peer-reviewed data, through spectra, through redshift confirmations, all pointing toward an early universe far more dynamic and aggressive than the serene era once imagined. In seminars, researchers spoke with measured tones. They paused often. Theories were proposed not with excitement but with a strange blend of curiosity and dread. For if JWST was correct, then the standard model of cosmology, arguably the most successful scientific framework ever constructed, might require revision. Not abandonment, but recalibration. The early universe might hold processes unaccounted for, or perhaps the smoothness of the lambda CDM timeline concealed hidden turbulence. The shock was not just scientific, it was philosophical. The universe, once thought to reveal its history through calm logic and slow evolution, was showing a past forged in haste. A past where matter gathered too quickly, where stars ignited too soon, where galaxies emerged before time itself seemed ready to host them. As JWST continued to observe, the contradiction only sharpened. The galaxies were real. Their distances were real. Their brightness was real. And so the foundational question began to crystallize. If the early universe was not slow, not patient, not quiet, then what force shaped its furious beginning? And what does that force mean for everything that came after? The shock was only the beginning. The deeper mystery was still unfolding, waiting in the darkness just beyond the light JWST had captured. As the first shock settled into the scientific community, a new phase began. One defined not by disbelief, but by forensic curiosity. The earliest images had shaken cosmology, but it was the detailed spectroscopy that transformed unease into profound mystery. JWST's instruments, built with precision exceeding any space telescope before it, were now tasked with peeling back the cosmic veil, revealing not merely shapes of ancient galaxies, but the chemical stories written in their light. Using NR spec and MIRI, astronomers began dissecting the faint photons that had traveled for over 13 billion years. What they found within those spectra was not simplicity, not the primitive elemental signatures predicted by theory, but fingerprints far too complex for the epoch from which they came. Some galaxies showed traces of carbon and oxygen woven into their spectral lines. Others revealed subtle signs of dust, microscopic grains forged in the explosive deaths of stars. These discoveries were troubling. Dust does not appear until generations of stars have lived and died, forging heavier elements in their cores, scattering them through space in supernovae. Yet these galaxies existed in a time when only the first stars should have been igniting, not dying in vast numbers. The presence of dust so early suggested an accelerated cosmic cycle, stars that formed, evolved, and perished with a speed that defied astrophysical understanding. Spectroscopy also revealed unusually intense emission lines, especially those associated with ionized oxygen. Such lines typically signal two possibilities: the presence of a vigorously star-forming galaxy, or the influence of a rapidly growing black hole. But here, the intensity was extreme. The early universe appeared to contain regions bathed in radiation so powerful that even hardened models of starburst activity struggled to explain it. To make sense of the data, astronomers turned to simulations. They fed the observations into updated versions of the most advanced computational models, Illustris-NG, Eagle, Fire 2, hoping to replicate the conditions under which such galaxies could arise. But run after run, the simulations faltered. Even when tuned to extremes, they produced galaxies too faint, too small, too chemically simple. It was as if the digital universes refused to generate the structures JWST was seeing. No matter how the parameters were twisted, the early cosmos in simulation remained reluctant, slow, and orderly, nothing like the chaotic, luminous reality that JWST had uncovered. Then came another revelation. Several of these ancient galaxies appeared to host ultra-massive black holes. In some cases, the black holes seemed to weigh nearly 1 billion times the mass of the Sun, despite existing less than 500 million years after the Big Bang. By the laws of known astrophysics, such masses should not have been attainable so quickly. Black holes grow through accretion and mergers, processes that take time, far more time than the universe had at those moments. Their presence implied something extraordinary. Either black holes were born from seeds far larger than theory allowed, perhaps from primordial origins, or the feeding and growth mechanisms in the early cosmos were more efficient, more violent, or more exotic than anyone imagined. Hints of gravitational lensing complicated the picture further. In some cases, background galaxies magnified distant objects, pulling their light into stretched arcs or small amplifications. Lensing could explain the apparent brightness of certain candidates. But even when lensing was accounted for, many early galaxies remained far too luminous and massive to fit comfortably within the standard model. Teams around the world embarked on cross-verification campaigns. Redshifts were recalculated, spectra were reanalyzed, contaminants were ruled out. False positives, objects whose brightness might mimic high redshift galaxies, were meticulously filtered. But the anomalies persisted. Independent confirmations through NIRSpec's high-resolution data and MIRI's mid-infrared signatures solidified the distances. These galaxies were not illusions. They were real, ancient, and profoundly inconsistent with the expected timeline of cosmic evolution. The deeper scientists looked, the more patterns emerged, patterns that felt like the fingerprints of a universe behaving in ways both familiar and deeply strange. First, the galaxies were unusually compact. Many packed tens of billions of stars into regions a fraction of the Milky Way's size. Their densities were extreme, suggesting gravitational forces far stronger than predicted for such young epochs. Second, their star formation rates were aggressive, bordering on violent. Some galaxies appeared to be producing stars up to 1,000 times faster than typical modern galaxies. Their light carried the unmistakable signatures of stellar nurseries igniting in furious bursts. Third, a strange uniformity emerged. These galaxies were not rare outliers. They appeared across surveys, Circe, Jades, Cosmos-Webb, scattered throughout the sky like ancient embers refusing to dim. The mystery was not confined to one field of view, it was woven across the cosmos. With every new observation, the early universe seemed less like a tranquil dawn and more like a storm, an era marked by rapid assembly, intense radiation, and gravitational wells forming with an urgency that defied the smooth mathematics of cosmic expansion. It became increasingly difficult to escape the sense that something layered lay beneath early cosmology, as if the familiar models touched only the surface of a deeper, more turbulent foundation. Some researchers suggested that the dark matter distribution in the early universe might have been far clumpier than predicted. If so, these dense pockets could have provided the gravitational seeds needed to rapidly assemble massive galaxies. But the clumpiness required to account for the observations bordered on the extreme, challenging even the flexibility of lambda CDM. Others speculated about exotic stellar populations. Perhaps the first stars, population 3 stars, were more numerous or more massive than previously thought. Such stars would burn intensely and die quickly, seeding galaxies with heavy elements and dust far earlier. But even this explanation required an efficiency that exceeded most theoretical limits. There were whispers too about new physics, modified gravity, early phase variability in dark energy, or unexpected interactions in the primordial plasma. These ideas were speculative, fragile, and rarely vocalized in public forums, but they floated through conversations at conferences and workshops, quiet as shadows cast on observatory walls. As more data accumulated, the early universe began to resemble a puzzle with too many edges and not enough center. Every piece added clarity, yet also deepened the contradiction. The galaxies were too mature. The black holes were too massive. The dust was too abundant. And the chemical signatures were too evolved. It was as if the cosmos, in its first half-billion years, had enacted a hidden chapter, an era of accelerated growth that left behind only faint, distant clues. Clues now captured by a telescope designed to see the unseeable. In the silence of research rooms, astronomers stared at the spectral lines glowing on their screens. Each peak and trough was a message from the early universe, carried across cosmic time like a whisper drifting through infinite darkness. And in those whispers, a single theme echoed over and over. The early cosmos was not the place theory imagined. It was stranger, faster, hotter, denser, a forge where gravity, radiation, and matter danced in unfamiliar rhythm. And beneath its surface, something remained buried. A mechanism, a force, or a process that shaped the dawn of galaxies in ways humanity has only begun to glimpse. The deeper the investigation went, the more the universe resisted explanation, inviting scientists to look further still, into a darkness where the oldest secrets were waiting. The deeper the instruments reach into the cosmic dawn, the more unusual the discoveries become. What once appeared to be isolated anomalies now gather into a pattern, subtle at first, like distant whispers carried across the void, then unmistakable, like thunder echoing across a darkening sky. The early universe, long assumed to be simple and slow, begins to reveal a hidden turbulence. Across the surveys returned from the James Webb Space Telescope, new structures emerge, structures that should not exist for hundreds of millions of years after the Big Bang. Some galaxies display hints of familiar architecture, elongated arms, rotating disks, and luminous cores. Not fully formed spirals, not yet orderly designs, but something restless, something halfway between chaos and symmetry. Their shapes suggest movement, rotation, gravitational organization, features that belong to a cosmos far older than the one JWST is looking at. In standard lambda CDM cosmology, this is impossible. Spiral galaxies take billions of years to sculpt themselves out of gravitational collapse and angular momentum. Their arms are fragile, easily disrupted by the violence of the early universe. Yet here, at redshifts beyond 10, lie fragments of rotation, like galaxies skipping ahead in their evolutionary timelines. The familiar rules feel suddenly uncertain, as if the universe is rewriting its own history. Beyond these unexpected shapes, the intergalactic medium, the vast ocean of diffuse gas between galaxies, begins to reveal signs of turbulence. Subtle distortions in spectra suggest motion, heating, and shock. The early cosmos was once pictured as quiet, gently cooling after its fiery beginning. But the new data speaks of disruption, of waves of energy racing across primordial space. The temperature variations appear sharper than predicted. The distribution of ionized gas hints at pockets of intense activity. Something was stirring the darkness more violently than theory had anticipated. Then come the quasars. Blindingly bright, impossibly distant, and growing faster than gravitational physics should allow, these early quasars ignite a new layer of the mystery. At redshifts beyond 7, beyond 10, even beyond 12, they gleam with the power of supermassive black holes already weighing hundreds of millions of suns. According to established models, such giants should take hundreds of millions, perhaps billions, of years to grow. Yet these ancient beacons shine as if they had been born massive, skipping the slow process of accretion entirely. Each discovery pushes further against the edges of the standard model, creating tension at the heart of cosmology. Dark matter halos, the invisible scaffolding holding galaxies together, appear more massive than simulations predict. Their shapes suggest early collapse, early clustering, and early gravitational efficiency, all happening too quickly. The cosmic web itself seems more organized, more filament, more dynamically matured than expected. The universe appears to have rushed toward complexity with astonishing speed. The notion that the early cosmos was a gentle dawn, soft, glowing, slow, begins to fade. Instead, JWST paints a picture of a storm-laden beginning, a universe racing ahead, assembling structures as if time moved differently. The expected sequence of cosmic history grows hazy. What was once considered foundational, the timeline of structure formation, the mass of early galaxies, the pace of chemical evolution, no longer seems secure. In the effort to reconcile these discoveries, new theories begin to surface. Some cosmologists turn to early dark energy, a hypothetical phase in which an exotic form of energy briefly accelerated the expansion of space. If true, density fluctuations could have grown sooner than expected, allowing matter to clump more quickly. This early dark energy would have faded before the universe reached its current form, leaving only subtle fingerprints. Others consider whether the gravitational constant itself might have been different shortly after the Big Bang. Even a tiny shift in the strength of gravity would dramatically alter how fast stars, galaxies, and black holes could form. The idea remains speculative, resting on the delicate intersection between cosmology and particle physics. But as contradictions deepen, no possibility can be dismissed outright. Another proposal suggests the expansion of the early universe may not have been uniform. Instead of a smooth stretching of space, there may have been regions of varied expansion, pockets where matter condensed faster, forming islands of accelerated growth. This would create patches of early overdensity, birthing galaxies, and black holes far ahead of schedule. Such uneven expansion would be difficult to detect billions of years later, yet its effects might still linger in the earliest light. Still others consider more radical possibilities, that fundamental constants, those mysterious numbers woven into the laws of physics, might not have been fixed in the earliest epochs. A slight variation in the fine structure constant or the speed of light, even briefly, could have reshaped the tempo of cosmic evolution. These ideas lie at the edge of theoretical physics, but the evidence is beginning to nudge researchers toward territories once labeled too speculative. Yet even these exotic explanations struggle to fully accommodate the most extreme findings. The early quasars, with their titanic black holes, remain stubbornly puzzling. Their masses defy growth models. Their light stretches the boundaries of what primordial accretion could accomplish. Some researchers propose massive seed black holes, possibly born from direct collapse gas clouds. Others whisper about primordial black holes, objects formed shortly after the Big Bang, before stars existed. If such black holes were sprinkled throughout the cosmos, the mysteries of early structure might be less surprising. But these ideas come with their own contradictions, challenging predictions from Big Bang nucleosynthesis and constraints from gravitational lensing surveys. Slowly, a broader pattern crystallizes. Every anomaly, every bright galaxy, every turbulent region, every ancient quasar, points toward a common theme. The universe became complex far earlier than expected. It did not creep into structure. It leapt. And with each new observation, the leap grows larger. The cosmic web, only a few 100 million years after the Big Bang, appears more intricate than simulations like Illustrious TNG or Millennium predict. Those simulations, built on the backbone of lambda CDM cosmology, struggle to recreate what JWST is seeing. They fail at producing enough massive halos so early. They struggle to make gas cool and collapse quickly enough. They cannot reproduce the brightness, the density, or the chemical enrichment observed. The data forces scientists to confront an unsettling possibility. The early universe might contain a hidden layer, something unaccounted for, something buried beneath the assumptions that shaped modern cosmology. Hints of this hidden layer appear in every direction. Compact galaxies, packed with stars at densities unknown today. Extreme star formation rates, reaching hundreds of solar masses per year in tiny volumes. Spectra showing signs of highly ionized gases, suggesting either violent radiation fields or exotic stellar populations. Even gravitational lensing, once suspected of tricking the observations, proves insufficient to explain the magnitude of the discrepancies. Step by step, the picture shifts. The early universe is no longer a peaceful canvas. It is a landscape of rapid growth, intense light, gravitational upheaval, and accelerated evolution. A place where matter clumps too quickly, where stars ignite too soon, where black holes grow too large, and where the cosmic web knits itself with inexplicable haste. As the evidence accumulates, a quiet suspicion begins to take root among researchers. Perhaps the Big Bang was not smooth. Perhaps the beginning was not uniform. Perhaps the first moments contained a pattern, a structure, imprinted before matter, before light, before time unfolded in the form we recognize. Some theorists whisper about pre-Big Bang physics, about quantum fields that left imprints as the universe inflated, about the possibility that the cosmos inherited conditions from something earlier, something hidden beyond the horizon of visibility. Most remain cautious. But the data continues to press. The early universe, once assumed to be simple, now stands revealed as one of the most complex eras in cosmic history, a storm hiding beneath the veneer of dawn. And every new discovery pushes the mystery further beyond the reach of standard cosmology. The escalation has begun. And the deeper the telescopes look, the more the early universe seems to resist explanation, as if guarding secrets older than time itself. In the wake of James Webb's unsettling revelations, cosmology enters a rare and fragile moment, an era where the familiar scaffolding of physics feels suddenly thin, as though the universe has chosen to reveal a deeper architecture beneath its surface. The early cosmos, once imagined as quiet, simple, and slow to awaken, now appears restless, crowded, and already ancient only moments after its birth. Confronted with galaxies that matured too quickly and black holes that rose too fiercely, scientists turn toward the realm of theory, searching for models flexible enough to hold this new and disquieting complexity. Their search begins with a force whispered into equations only in the last few years, a phenomenon known as early dark energy. In classical cosmology, dark energy enters the cosmic story late, accelerating the expansion of the universe billions of years after the Big Bang. But some physicists now propose a brief, earlier pulse, an ancient flicker of repulsive force that acted just after inflation ended. This early dark energy would have pushed matter apart for a short time, creating pockets of lower density that later collapsed more violently. In such regions, gravity would amplify its pull, allowing stars and galaxies to ignite sooner than expected. If JWST's anomalous galaxies lie within these pockets, then the cosmos may have carried scars of an early, forgotten acceleration, an echo of a force that briefly rewrote the tempo of creation. Yet early dark energy remains elusive. Its traces would be faint, buried within the cosmic microwave background, detectable only as subtle distortions in the distribution of primordial ripples. Others look to a different actor in the cosmic play, dark matter, the invisible mass that scaffolds galaxies and binds the cosmic web. For decades, cosmology relied on a cold and silent version of this substance, slow-moving and indifferent, forming structures gradually. But JWST's early galaxies seemed to demand a more assertive form. Perhaps dark matter was not cold, but warm, moving with the faintest thermal breath, gathering into smaller and faster-forming halos. Or perhaps it interacted with itself, self-interacting dark matter, capable of transferring momentum, creating denser cores that could seed rapid collapse. If dark matter clumped more efficiently than expected, it could have provided the gravitational wells needed to build mature galaxies in impossibly short timescales. Several teams have begun adjusting simulations to test this idea, altering dark matter's properties in ways that produce earlier structures. But so far, the models strain to match the density and luminosity that JWST sees. Something still feels missing, as though gravity had a secret ingredient not yet captured by equations. Then comes a theory as old as cosmology itself, yet reborn with every new generation of data: the possibility of primordial black holes. These are not the remnants of stars but relics from the Big Bang, forged in the first fractions of a second when extreme density fluctuations could have collapsed into singularities. If such black holes existed, they could serve as the seeds of galaxies, gravity wells around which gas would gather, cooling into stars with unprecedented speed. JWST's detection of ultramassive black holes at redshifts greater than 10, devouring matter at the center of early quasars, gives this theory new weight. A primordial black hole, already massive at birth, could explain how such titans arose when the universe was still in cosmic infancy. Yet direct evidence remains slippery. These black holes leave no distinguishable signature from those formed later, making their origins a matter of inference rather than observation. Still, some suspect the universe itself may have behaved differently in its youth. That perhaps the fundamental constants, the deep rules governing reality, were not as fixed as they appear today. If gravity were slightly stronger during cosmic dawn, or if the strong nuclear force bound atoms with just a little more intensity, stars could ignite faster, galaxies could condense earlier, and heavy elements could arise with surprising haste. Variations in constants are not impossible. Certain theories of grand unification predict that forces can evolve. And even a change of one part in a trillion, lasting only for a brief epoch, could radically alter the pace of early structure formation. But observational constraints from primordial nucleosynthesis and the microwave background leave little room for such variations, making this theory both tantalizing and dangerous to cosmology's foundations. As scientists probe deeper into JWST's data, another possibility emerges from the physics of inflation, the brief, catastrophic expansion that set the initial conditions of the universe. Standard inflation smooths everything, erasing irregularities. But alternative models propose a more turbulent origin, where inflation produced density spikes, sudden surges of matter that later collapsed into hyperdense regions. These regions could have become cosmic overachievers, forming stars and galaxies at breakneck speed. In some inflation models, these spikes come from quantum fluctuations amplified unevenly, leaving behind what physicists call multiverse fossil signatures, imprints of other inflationary regions that brushed against our own. If JWST's early galaxies lie within these fossil regions, their strange maturity could be the legacy of ancient quantum storms. Related to this idea is a lesser-known but increasingly discussed scenario: cosmic reheating anomalies. After inflation ended, the universe had to warm back up, a process known as reheating, where energy from the inflaton field was transferred into particles. If reheating was uneven, some regions could have been endowed with greater thermal energy, triggering earlier gravitational collapse. These cosmic hotspots would become overachievers, while neighboring regions would remain slow and sparse. JWST may be peering into one such hotspot, a patch of the universe that was born with excess ambition. This theory remains speculative, but it fits the pattern emerging from early JWST surveys: a cosmos that was not uniform, not gentle, not simple. But there is one final theory, one that sits at the edge of cosmology, where equations blur into philosophy. It suggests that the early universe was not merely shaped by the Big Bang. It inherited something from before. In models of loop quantum cosmology, space-time does not begin at the singularity but bounces, collapsing from a previous universe and expanding into this one. In ekpyrotic models, our universe forms from the collision of higher dimensional branes, each collision leaving faint imprints on structure. In some cyclic cosmologies, every universe passes down subtle arrangements of density, a cosmic memory carried across eons. If this were true, then JWST may be witnessing residual structure, faint fingerprints from a universe long dead. Density variations passed through the bounce could have created regions predisposed to rapid formation, giving rise to galaxies that already feel ancient in a cosmos scarcely born. These ideas remain the most speculative, yet they linger because they explain something deeper than early galaxies. They offer a reason why the universe seems almost too prepared, too organized, too ready. As these theories collide and intertwine, cosmologists find themselves in a place both exhilarating and unsettling. No single explanation fits every observation. No model captures all of JWST's anomalies without creating cracks elsewhere in physics. The early universe, once thought to be a simple dawn, now resembles a maze of hidden corridors, each theory a lantern illuminating only a fraction of its depth. And in this uncertainty, a quiet realization emerges. JWST has not merely revealed earlier galaxies. It has revealed the limits of what humanity thought it understood. The cosmos, vast and ancient, still guards its deepest secrets. And with every new image, the boundary between knowledge and mystery shifts a little further into the dark. In the months and years following James Webb's first deep-field images, the scientific world enters a strange twilight between certainty and doubt. The telescope continues its silent work at the distant Lagrange point, orbiting in a halo of gravitational balance, staring deeper into the past than any instrument before it. But now, every new image carries a trembling sense of consequence. Each faint red smudge, each elongated arc of distorted starlight, each spectrum carved from ancient photons becomes a piece of evidence in a growing cosmic investigation. And so, the effort intensifies. JWST's near-infrared detectors, tuned to wavelengths stretched by billions of years of cosmic expansion, sweep across the sky with deliberate precision. Programs like JWST, JADES, Primer, and Cosmos Web expand their mosaics across the heavens, gathering galaxies so faint they appear almost imaginary. Webb spectrographs, NR-SPEC and MIRI, dissect these galaxies one by one, breaking their light into chemical signatures that whisper of age, temperature, metallicity, and motion. In these signatures, astronomers find clues not only to the objects themselves, but to the forces that shaped the early universe. Yet with each dataset, the puzzle grows more intricate. Some galaxies, when examined more deeply, appear even older than initial measurements suggested. To test these findings, scientists follow twin paths, observing the sky and recreating the sky inside their machines. More pointed campaigns begin to focus on the most controversial candidates, those with extreme redshifts, compact sizes, or luminosities so high they border on theoretical impossibility. JWST's spectroscopic mode becomes the primary weapon in this search, offering direct confirmation of distances that photometric guesses only approximate. As redshift confirmations mount, it becomes clear that the anomalies are not a trick of light, not a miscalibrated filter, not an eager misinterpretation. The universe truly formed structures earlier, faster, and more aggressively than standard cosmology predicted. Still, astronomy has learned caution from its own history. And so the scientific world looks outward, to the missions that will join JWST in the coming years. ESA's Euclid mission, launched to map the geometry of dark energy and dark matter, now scans wide fields of sky in optical and near-infrared light. Where Webb provides depth, Euclid provides breadth. It charts billions of galaxies, measuring weak gravitational lensing distortions across cosmic time. These data will help determine whether dark matter behaved differently in the early universe, forming denser halos or collapsing sooner. Euclid's precision cosmology may confirm whether the standard lambda cold dark matter model bends or breaks in the face of JWST's discoveries. Then comes the Nancy Grace Roman Space Telescope, NASA's next major observatory, designed to perform wide-field infrared surveys with resolution approaching JWST's but spanning areas hundreds of times larger. Roman will hunt for early galaxies by the thousands, not the dozens, testing whether Webb's observations reflect a universal cosmic pattern or a rare statistical fluctuation. Its sensitivity to the faint glow of distant supernovae may also reveal whether cosmic expansion behaved differently in its opening chapters. But satellites alone cannot solve the mystery. The early universe may have hidden its secrets in the tremors of spacetime itself. In the coming decade, the Laser Interferometer Space Antenna, LISA, will open a new window. It will listen not to light, but to gravity. As 3 spacecraft orbit the Sun in a triangular formation millions of kilometers apart, they will sense the subtlest ripples in the fabric of spacetime, echoes of massive objects merging in the ancient dark. If primordial black holes existed, black holes born in the first moments after the Big Bang, LISA may detect their collisions. Such mergers would produce gravitational waves unlike those from black holes formed by collapsing stars. Their frequencies, amplitudes, and mass signatures would carry the unmistakable imprint of a universe-forming structure too early. A single detection could tilt the scales in favor of the most radical theories. Yet the investigation does not stop in space. Deep beneath the Earth and within vast underground caverns, particle physicists search for the invisible matter that shapes the cosmos. The Large Hadron Collider, still probing the limits of the Standard Model, continues to search for evidence of dark matter interactions, recoils, missing energy, or exotic decays. Its successors, future colliders planned in Europe, China, and the United States, aim to push these boundaries further. If dark matter is more dynamic than assumed, if it interacts with itself or with normal matter in unusual ways, these colliders may reveal it. Meanwhile, the universe's earliest structures may be mapped not through light, but through the faint whisper of ancient hydrogen. Across deserts and remote plateaus, radio observatories prepare for a new era of 21-centimeter cosmology. Instruments like the Hydrogen Epoch of Reionization Array, HERA, the Future Square Kilometer Array, SKA, and a constellation of global experiments aim to measure the stretched signal of neutral hydrogen from the cosmic dawn. These signals, faint, buried beneath Earth's interference, carry information about the first stars, the first galaxies, and the first black holes. If early structure was unusually rapid, the 21 centimeters signal will show it. Regions of intense heating, ionization, or turbulence would indicate a universe racing toward complexity faster than gravitational models allow. The pattern of this ancient hydrogen will either affirm or contradict JWST's revelations. On the computational frontier, entire universes are born inside supercomputers. Simulations once governed by the assumptions of cold dark matter and slow galactic growth now undergo revision. Computational astrophysicists feed JWST's early galaxies into their models, adjusting parameters, reconstructing physics, and rewriting the initial conditions. They test scenarios where dark matter clumps faster, where inflation produces density spikes, where primordial black holes populate the early cosmos, and where radiation from the first stars reshapes their surroundings with unexpected ferocity. Some simulations collapse under the weight of these changes, failing to reproduce real-world structures without creating contradictions elsewhere. Yet others begin to hint at possible solutions, universes where early growth is not only possible, but inevitable. These virtual universes become laboratories for testing the foundations of cosmology. If a simulation can produce the galaxies that JWST sees, and still match the cosmic microwave background, gravitational lensing surveys, and large-scale structure maps, then cosmology gains a new foothold. But if every attempt fails, a deeper revision may be required. And yet, the scientific world remains cautious. 3 possibilities dominate the ongoing debate, each carrying its own weight and consequences. The first is the simplest: a calibration error. Could JWST's instruments be subtly misaligned, its detectors influenced by unknown artifacts, or its redshift calculations skewed by dust? Multiple teams scrutinize the data, comparing independent reductions, cross-checking with ground-based observatories, and testing every assumption. But the anomalies persist across filters, across instruments, across methods. Calibration seems unlikely. The second possibility: a misunderstanding of galaxy evolution. Perhaps early galaxies can grow faster than models predicted. Perhaps star formation in dense environments is more explosive, more efficient, more chaotic. Astronomers explore this option carefully, modifying stellar population models, adjusting estimates of mass-to-light ratios, reanalyzing how dust affects brightness. Yet even the most generous interpretations struggle to explain the observed density, maturity, and mass of these ancient objects. And then remains the final, most unsettling possibility: a crack in the universe's foundations. A sign that lambda-CDM cosmology, while immensely successful, may not describe the full story. A signal that gravity, dark matter, or the early expansion of spacetime operated with greater complexity than humanity's equations have yet captured. As JWST continues its watch, and as new instruments rise to join it, the scientific world approaches a threshold. What lies ahead is not merely the refinement of a model. It is the possibility of a new chapter in cosmology, a recognition that the universe, from its first breath, followed patterns more intricate, more turbulent, and more ambitious than anyone expected. The race continues. The data grows. And somewhere in the ancient dark, the truth waits. In the quiet aftermath of discovery, when data settles like dust across the surface of human understanding, a different kind of silence emerges. It is not the silence of space, nor the frozen stillness of JWST drifting through the cold halo of L2. It is the silence that follows realization, the moment when knowledge expands faster than certainty can keep pace. In this silence, the universe seems to lean closer, revealing not answers, but deeper questions. For as long as humans have looked upward, the sky has behaved like a mirror. It has reflected the limits of perception, the boundaries of imagination, and the fragile daring of curiosity. Yet now, with light older than galaxies pouring through polished gold and carbon surfaces, the mirror has changed. It no longer shows what humanity expects. It shows what the cosmos actually is: strange, intricate, and written with a complexity far older in pattern than the age engraved in its expansion. Across continents, in labs and observatories, quiet rooms glow with the faint blue of screens as researchers try to understand why the early universe appears so mature. Why fully formed galaxies spiral in epochs where only embryonic clumps of gas were expected? And why supermassive black holes, cosmic engines that should have taken hundreds of millions of years to grow, already burn at the dawn of time? The numbers offer no comfort. They simply affirm the depth of the mystery. Spectral lines whisper of heavy elements that should not yet exist. Photometric redshifts push formation timelines to their limits. Simulations press against computational boundaries, reshaping the early cosmos again and again, trying to match what the telescope has seen. Each attempt brings them a little closer to understanding, yet every solution seems to unravel another thread. In moments like these, the universe itself seems to stand at a crossroads, not changing, but revealing the limits of existing belief. For if galaxies matured too quickly, then the cosmos is not merely a place of vast distances and long ages. It is a system of hidden efficiencies, of shortcuts written into the earliest physics, of patterns older than the fabric they reside in. It suggests a universe not young and chaotic, but ancient in design, bearing the fingerprints of processes yet unknown. And so, a broader reflection arises: how small humanity remains before such immensity. Not in size, but in comprehension. The cosmos does not behave according to expectation. It behaves according to its own deeper order. Every generation of scientists writes a new version of cosmic history, only to watch the next generation rewrite it again. These revisions are not failures. They are the natural rhythm of discovery, the slow, unending process by which the universe teaches, withdraws, and teaches again. For 200,000 years, Homo sapiens have lived beneath the cosmos, tracing shapes into the sky, believing they understood the rhythms of creation. But the deeper instruments reach, the more distant the truth becomes. The dawn of galaxies now appears more crowded, more luminous, more evolved than any model predicted. The early cosmos no longer resembles a child taking its first steps. It resembles an adult hiding its past. And what does it mean to live in such a universe? One where certainty bends and the cosmos resists being understood? Perhaps it means that curiosity is not simply a human trait. It is a necessity, a force as essential to civilization as fire or language. A quiet recognition that knowledge will always expand faster than comprehension, and that the pursuit will never be complete. The cosmos is not obliged to simplify itself so that humanity may understand it. Instead, it invites humanity to grow into understanding. And so the questions become philosophical, not just scientific. If the earliest galaxies were already complex, then what does beginning truly mean? Does the Big Bang mark the first moment of existence, or merely the first moment the universe became measurable? If primordial structures were seeded before the first atoms formed, then perhaps the Big Bang was not the birth of everything. Perhaps it was only a transition, a moment when an older reality folded into a new one. In theoretical physics, such ideas are not dismissed lightly. Loop quantum cosmology suggests the universe may have rebounded from a previous contraction. Ekpyrotic models imagine entire worlds colliding across higher dimensions, each impact birthing a new cosmos. Some interpretations of inflation propose that countless universes bloom and fade like sparks rising from a primordial fire, each with its own laws, each leaving faint imprints on the fabric of its neighbors. If this is true, if the universe carries a prehistory, then JWST may not be observing the first galaxies. It may be observing the remnants of something older. Fossil structures carried through a cosmic transition. Patterns inherited rather than created. But even if such ideas remain speculative, their emotional weight is undeniable. They expand the human sense of scale, stretching imagination to its limits. They suggest a cosmic lineage far grander than a single moment of expansion. They suggest a universe with memory. And through all this, JWST continues its silent work. Orbiting the Earth, Sun L2 point, shielded from heat and light, it listens to the faintest whispers of the past. It gathers photons that began their journey before the Milky Way existed. It traces the quiet arcs of cosmic dawn, recording the birth cries of galaxies and the murmurs of collapsing stars. It does not judge or interpret. It simply reveals. And in this revealing, it becomes something more than an observatory. It becomes a storyteller. From its cold vantage point, the telescope transforms ancient light into narrative. It shows that the cosmos is not a static map but a living history, one that grows more mysterious the deeper it is explored. It reminds humanity that understanding is not a destination but a horizon, always retreating, always inviting further pursuit. And so the chapter closes on a quiet truth. The universe is larger, older in spirit, and more intricate in structure than any generation has imagined. Its earliest epochs, once thought simple and unformed, now glow with the complexity of a cosmic garden blooming before its time. To live in such a universe is to accept that mystery is not a barrier, it is a companion. It is the force that drives humanity to build telescopes, craft equations, and whisper questions into the dark. It is the reminder that the cosmos does not yield its secrets willingly, but it does yield them, one photon at a time. In the end, the greatest truths still sleep in the light waiting to be seen. And somewhere, adrift in the cold clarity of L2, a mirror of gold and shadow continues to gather that light, pulling back the veil on a cosmos whose story is far from finished. The universe is not done surprising humanity. It is only beginning.